Ladies and gentlemen, hello and welcome, coming again to you not quite live from One Take Studios, where today's topic is normal probability distributions. Not to be confused with standard normal probability distributions, alright? So this video does not include standard stuff, so if you're looking for that, please look someplace else. Just want to look at what is considered to be a normal curve. This is something that's referenced a lot. People talk about a bell curve and maybe don't always know what they're referencing. So a normal curve is the graph of a probability distribution when it has been normalized. What does this mean? Well, this means that the graph itself is going to have the highest point over the mean. So everything is centered over mu. This graph has to be symmetrical. If it's skewed in any way, it's not normal. Not normal. The horizontal axis over which this curve is floating is actually an asymptote, hence I use the word floating. Please understand, the word asymptote is spelled with one S. It is not a bad word, and yes, the P is silent. And you will have inflection points, changing of direction in your curve, over mu plus 1 standard deviation and mu minus 1 standard deviation. If that all sounds like complete Greek to you, let's look at this, okay? So let's draw it and put it together. Now, I'm asking you to forgive me. This is my sketch. I am not perfect. My drawing skills are not perfect. In fact, I've never actually had an art class, as some of you probably can tell. So, ladies and gents, this is my drawing, to the best of my ability. I'm going to use this line as my x-axis. We only have one axis for these. These are not like coordinate plane kind of things. A couple things that you should notice. This is the highest point of my graph, and according to this, the highest point has to be over the mean. Therefore, the mean must be right here. All right, so everything is centered over the mean, over the highest point. This is supposed to be symmetrical, and gosh darn it, I did a pretty good job. It's probably not perfect, but it looks like it's pretty symmetrical. This is an asymptote, which means that the line will approach, the graph will approach the line for forever. So notice the graph is approaching the line, but the graph never actually gets there. You will see a lot of graphs that are done online and in textbooks where it shows that this line actually touches, like they meet each other. And truthfully, they will get insanely close to the point that the naked eye cannot tell the difference. But if you are in one of my classes, you will leave that little bit of breathing room right there so that I know that you understand that that's an asymptote. All right? So this is going to be hovering, and it's going to grow closer for all eternity, but not going to quite connect. That's what an asymptote is. All right, inflection points over mu plus and minus sigma. All right, so roughly where this goes from curving outward to curving inward, I'm going to say is about maybe right there, and about maybe right there. Could I be off? Yes. Again, this is a sketch. What does this mean? This means that this spot right here is going to be 1 standard deviation above the mean. And this point right here is going to be 1 standard deviation below the mean. So notice, below is negative, above is positive. This is a number line. It is. And it gets counted in standard deviations. So if this is my 0, so to speak, on my number line, this is 1 standard deviation. This would be 2 standard deviations. This would be negative 2 standard deviations. Can I go to 3? Yeah, the curve does keep going, it keeps approaching, but this is what we're talking about, all right? This would be considered a normal curve, not because it looks normal, because there's lots of curves that probably look normal, but because it actually meets these criteria. So that is going to be our difference there. All right, couple of additional things for you to know. You know what? Hold that thought for a second. Let's have a little bit of fun. Let's draw things that are not normal. What if I do a graph that looks like this? Boom. Is that normal? No. Why not? It's not symmetrical. What if I do this? It's kind of symmetrical. It's got the asymptote. That part's okay. Ooh, but it has to have a single highest point, and it's lumpy, and lumpy's bad. All right, this has multiple inflection points. This is not going to work. What if this is my axis, and my graph does this? It crossed the asymptote. That's bad. That's not going to work. So these are all pictures of things that absolutely would not be normal curves. I've probably heard it best described like this. If you've ever played on the beach with dry sand, All right, pick up a handful of dry sand and let it fall between your fingers to the ground. It creates this natural mounding hill. That's the look that we are going for a normal curve. Okay, now that we got that out of the way, other things that you should know. The area beneath this curve is always 1, thus making a density curve. So this will always have an area of 1. So that means that if the standard deviations shrink or expand, it does not matter. This still represents an area of 1. Why is this brilliantly wonderful? Because this actually shows us everything that could possibly happen in our probability distribution. Therefore, if we can find the area under the curve, we actually then also know the probability of something happening based on its location under the curve. So area and probability are actually going to be the same thing here. This is the biggie right here. I'm going to show you an image of this in a moment. This is huge. Okay, this is referenced quite frequently. The empirical rule, kind of based on the work that we've seen from Chebyshev, that if I am within 1 standard deviation of the mean, here's the mean, here's 1 standard deviation. So if I go from here to here, I am saying that 68% of the data values in this set are between those 2 lines. If I stretch that a little bit farther and I go out to 2 standard deviations from here to here, that's going to be 95% of my data. And notice already how small this tail is, how little area is here and how little area is here. That's because 95% of the data is here. Wait a minute, if 95% of the data is here, how much is here? And how much is here? If this is symmetrical, if 95% is used up, that means that there's 5% remaining. So this little section right here is 2.5%, and this is 2.5% of my data. And again, if we stretch it out to 3, because the tails get so close to the end of this, 3 standard deviations away, we are now up to 99.7%. All right, so I'm going to show you what this looks like. And quite frankly, you should probably not have notifications on your screen right now. There we go. You should probably take a good look at this and copy it down or find one to print out for yourself because you're going to be referencing this quite frequently. Ladies and gentlemen, this comes from a website, and so I borrowed it. We're talking, here's our normal curve. You can see, like I said, a lot of books and stuff will show it actually meeting the asymptote. That's because it's going to get insanely close. And this has beautiful labels for us. Specifically, they're actually more accurate than a lot of textbooks I've seen. 68% is what I just told you. It's technically 68.27. But we are saying that in this neutral colored zone here, 68% of our data lies. Now, just using 68% for a second, let me ask you this. How much data is right here? How much is between 0 and 1? Well, if this whole area is 68%, this would be 34% here and 34% here. Break it down. If everything in the blue and neutral colored areas here, the light blue, is 95%. All right, well, kind of piece it together. You can figure out how much is going to be in each section. What's 95 minus 68? Cut it in half. There's a piece of it over here. There's a piece of it over here. You are going to want to have this image where you can reference it frequently. And this is the empirical rule that I just referenced but did not draw for you because, again, my drawing skills leave something to be desired. All right, so make sure that you've got a good shot of that someplace where you can reference it. I'm going to jump back over to here. There we go. Okie dokie. Now, just to give this a little bit of personal touch, a little bit of context to go with it, what might this mean for an application? So, I've decided that there's a box of Crunchios. If this is an actual cereal, I'm sorry. I'm pretty sure I made it up, but who knows. Crunchios cereal boxes contain a mean of 12 ounces of cereal with a standard deviation of 1/2 ounce. Okay. What does this mean? This means that not every box of cereal contains the exact same amount of cereal. There could be some fluctuation a little bit here, some quality control stuff, because it's put together by machine and assembled, and so there are tolerances, of course, but there could be things that are a little bit off. So here's what I want to know. What is, that says is, the probability of getting a box with more than 13 ounces of cereal in it? What is that probability of getting a box of cereal with more than 13 ounces? Okay, I'm going to sketch this. to me, my brain really likes to see the pictures that go with it. Here's my normal curve, or a sketch thereof. This is the mean, which I know to be 12, so I'm going to label it as 12. And I'm counting by standard deviations of 0.5, so we'll call this 12.5, and that would make this 13. So notice I am counting by standard deviations, which is what you're seeing here. You go up by a standard deviation, you go up by another one. Since the standard deviation is 0.5, we go up by 0.5, we go up by 0.5 again. Same thing other direction. This is going to be 11.5, this is going to be 11, and so on and so forth. So notice my question happens to correspond with one of these distances, where I am a specific distance in standard deviations away from the mean. So I am here right now, and I'm looking at what's the probability of a box with more than that. That's this guy right here. I want to know what is the area in this tail so that I can find the probability in this tail. Well, okay, so think. If this is the mean, this is 1 standard deviation, this is 2. 2 standard deviations, 95%. That means that from here to here, this whole middle section here is 95%. That means that there's 5% remaining to go in the tails, which is a lot like the problem I just referenced a moment ago, saying, all right, what's going to happen with this? Well, if this is 95% and this is 5% total, this is going to have to be 2.5% on the ends. So the probability of me getting a cereal box from Crunchios that is more than 13 ounces is actually 2.5%. So that's what an application might look like. They will give you something referencing the mean, so you know where to center everything. They will tell you a standard deviation, and you use that to count on your axis, and then you just play with the percentages to kind of figure out what goes where. All right, it's not super crazy, at least as crazy as it looks, and it's something that, again, you just get more comfortable with over time. All right, so enjoy. Thanks.